Okay, so welcome back. And it's my great pleasure to introduce again Giancarlo, who is going to give his fourth lecture on wall surfaces. Please, Giancarlo.
Thank you. This is working? Okay. So I would like to start with a summary of how you run MMP. You know, I gave you last time the tools, and now I would like to show you the picture. So remember that my surface is a normal projective surface with only wall singularities. And this is inside a threefold, which is fiber over a disk. And this is pointing a distinguished point, 0. And this is the Q-Gorenstein deformation, smoothing. And so this WT, like any fiber over a T that is not 0, is non-singular. And this is this picture is a Q-Gorenstein smoothing. So this is the object to which I will run MMP. So I have something like that. And then there is a canonical class, which I always take not here, but here. So if KW nef, then this is nef for every T. And then I told you last time how to more or less classify the situation of WT when this W is really singular, so there are some wall singularities. Because otherwise, this is a smooth deformation, and here I would put the Enriquez classification. And then you have Kodaira 0 for the general fiber. So 1 and 2. And I told you that these, and here you have Enriquez surfaces. And here you have elliptic fibrations over P1. So more or less the picture for these two Kodaira dimensions are elliptic fibrations. You know that Enriquez surfaces also have elliptic fibrations. And you get this degeneration also as a, so this is going to be also an elliptic fibration, but now singular. And then this is more mysterious, so I will talk about that in a moment. This is okay. And so what happens if it's not nef, then we run MMP. Then I told you that there exists a gamma minus, let me call it gamma minus, which is a P1, C, inside of W, with KW dot gamma minus negative. Remember that this is singular, so this is a negative rational number. And then you have options. So one option is that this gamma minus square is negative 2. The other is gamma minus square equals 0. And I will tell you what happens here. And this is going to be the main topic today, what happens when gamma minus square is positive. And here I mean, you have a situation like this, and for these cases, you don't have these situations. So I really want to look at the minimal situations when you have a negative curve with respect to canonical class, like ruled surfaces and P2 in the classical case. But if this is happening, then you have two options. So if this is happening, then we have a K1A situation, like last time, K2A situation. And they are divided into flip divisorial contraction. And in a flip, you have a situation like this. So this is my W. And you have this gamma minus here. In the case of K1A, you have one singularity on gamma minus for the surface. And the K2A, you have two. Let me put two, something like that. And so here you have your WT. And this curve disappears here. You don't have any lifting of the curve. And then you have to perform, so a situation like this, and then you perform a flip. I don't have one. Let me move this a little bit more. And so now you have a flip. So this would be like the flip, and this is the gamma positive, the W positive. And my picture is like this, so it's very similar to this, where you have now a positive curve. This is negative. This is going to be positive with respect to canonical class. And here you might have one, two singularities, or maybe you don't have singularities. And the WT here and here are isomorphic. Nothing happens really on general fibers. Everything is happening on W, on the central fiber. And this is the flip. And also remember that this is over, so you can contract this curve or you can contract that curve, and this is over a cyclic quotient singularity. So when you contract, you get some cyclic quotient singularity. And this was a P resolution of that cyclic quotient singularity. We call it extremal P resolution.
So you are assuming that gamma minus is extremal ray, right?
Extremal ray, yeah, and negative. Yeah, this is an extremal ray. Okay, and also remember that here you have a unique situation for the flip. This is unique. But here you have the Mori trains. So there are deformations of this neighborhood, which are not of finite type. These go to infinity, and this is, I was talking to you about Mori trains. Okay, otherwise, you have a divisorial contraction. And the situation is similar. You have the W with a negative curve. So this is my gamma minus, negative curve. You have some singularities, Wahl singularities. But now in the general fiber, you will have a lifting of this curve, which is going to be a -1 curve. And so you produce a divisor. And this divisor is contracted to a W surface. So there is a contraction here. This is maybe a Y prime, no, W prime, I don't know. And now you contract this point to a Wahl singularity. This is Wahl. And here you contract this -1 curve to a smooth point. So this is Castelnuovo. The general fiber is Castelnuovo, like a blow-up. And here you have this other situation. This is WT prime. This is very small now. But this situation and that situation is a W surface. Remember that I put this name to this object. And then you ask if in this case we have the canonical class is not Neff, then you come back here, this case or that case. Otherwise, this is Neff, and now you are here. So this is the summary. This is the change. So you only have Castelnuovo in the classical case when you have something non-singular. Now you have these two situations. Flip, divisorial contraction, Mori trains. And here, because of this family, over this surface, you have this kind of, I would like to call it like a fractal of Mori trains that are connected in some way. So this is going to be a main point on what I'm going to say here and problems that we have in mind related to this case. Okay, so let me tell you about this now. So here, when the codary dimension of the general fiber is 2, Then we have the situation of a big NF canonical class. And then you can think in this way. We have the deformation, but now you want to go to the canonical model. So there is a way to go to canonical model here, and you have a deformation W can, and there is a birational map from W to W can, and okay, we have this. Well, this is over that 0 also, and then this. You can think about that as a small disk in the KSVA compactification of modular space of surfaces of general type with, we fix k squared and the Euler characteristic of the surface. And by the way, remember that here there are invariants that stay constant. For example, k squared, pg, q, and the topological Euler characteristic are all constant. And what is this KSVA modular space? So you have the Giesecke, you have several components. This is the Giesecke modular space of surfaces of general type with these two invariants fixed. And then Collard and Schaeffer-Varron propose a compactification of this. So this is a quasi-projective variety. Oh, maybe scheme. Because there are a lot of singularities. You might have components that are non-reduced. Nothing is nice on this modular space. And then, typically, and then Collard, Schaeffer-Varron propose a way to create a projective scheme, which is projected because of Alexiv. That is why we have KSVA, Alexiv is A, projective scheme that compactifies the yellow part. But as you see here, you might have components with surfaces that are not smoothable. So it's not like the closure of this quasi-projective variety. But a situation like this W can, then would be like a small disk that goes from the yellow and crashes to the red. So this is my situation. Now, yes, there are. So I was going to say something about that. Not every singularity is, so by the way, this W can has only T singularities. And so you might think the replacement of ADE singularities, when you have the classical situation, you go from smooth to ADE. Now you go from Wahl to T singularities. This is the replacement. But not every singularity is T singularity on these surfaces. And also they might break, and they break. They break in general. So more officially, they have the so-called SLC singularities, semi-log canonical singularities. In particular, if you have something normal that didn't break, that is normal also, you have the log canonical, which is a bigger list. For example, every quotient singularity. But if you are in this closure and you have quotient singularities, by definition, they must be T singularities. And also, the dualizing chief is ample. Okay, so you have more. We are looking at a certain parts. And not necessarily like closure. Maybe we are here with only T singularities. Maybe the surface is not smoothable. Okay? Example. So now I would like to show you what do you see when you run this? So how is it done? So with an example. So say that we take a situation like this. So again, an elliptic vibration, but it doesn't need to be. So don't have them. So many examples are constructed with elliptic vibrations because on elliptic vibrations we have several obvious rational curves. But you might start with P2 and an irreducible curve and do certain blow-ups, and that happens, okay? And it's not connected with any elliptic vibration in principle. So say that we have a situation like this. I will put 3 nodal fibers and an I4 fiber, and then, let me see, a section and another section, like that. So this is -1 curve, -1, and they are -2s, and here 0, 0, 0. And now the magic, you do certain blow-ups. So let me see. So this is going to be -2, -2, -2. So maybe I will draw, and then I will explain. It's going to be -6, -2, -2. Okay, I don't want to take that section, but this. So if you blow up twice, here and here, this -1 becomes -3. Then this is -5, and -2, and -4. And this is -7, I think. So -1, and then you have 6, yeah, -7. Okay? So now, you see this curve, this, and that. And that is a Wahl chain. It's 7, 2, 2, 2. This is 6, 2, 2. This is 2, 5, 3. And this is a 4. So you might contract these 4 Wahl chains. And then I told you that if k squared, so k squared here is 0. K squared here is, now we need to do, so we need to see how many times I blew up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then to compute, so you know, artin, we go to a contraction. And for example, maybe you want to contract the 4 chains, and then you need to add the length. So you have 4, 3, 7, plus 3, and plus 1, 4, 3, 3. So it would be 11. So I get something 0 here. Wait a second. Yeah, so, well, yeah, but, well, this, oh, I see. Yeah, sorry. This is coming, so this is not -4 because I did 2 blow-ups. So here there is a 2, a -2 curve. So this is not a nodal here. So it's something like this. Okay, now it's -4. So I didn't do that blow up. So it's, this is minus 10. And so plus 11 is 1. So this would be a Godot situation. So W, contraction. This is a minus 2. Hmm? Yeah, but I don't do anything with that, so I can't. What next one? This? No, it's minus 4 because I have this blow up and that blow up. Yeah, minus 4. Let me color that minus 4. Then you contract, and this W has K squared equals to 1. PG is 0. Q is 0. And actually, if you compute this obstruction, as I told you some day ago, then this WT would be a simply connected, in this case, simply connected Godot surface. So in the modular space of Godot surfaces, you are looking at something like this.
For this obstruction thing, you were allowed to forget about some -1 curves?
Yes, yeah. So you start, or maybe I can recall, you have two complete fibers, then the obstruction is 0. Then you add this ADE and this other ADE, so it stays 0. And then you add these two sections, 0. And now you do the blow-ups, and it stays 0. So you have this Godot surface. But now, so I would like to, here there are no obstructions. You have a surface like this with 4 singularities. And there are no obstructions, so now you can choose, well, maybe I want to smooth all of them except this one, the 4. And I would like to know what do I get? In the sense, I resolve the singularities, and I want to know the minimal model of that, okay? Maybe forget about that and just erase this curve. I don't want to use it. In this case, the canonical class here is nef. Okay, you can also compute that. Say that now is white, so I'm not using that. And what happens is that now when you contract, so this is going to be another W prime. So now the contraction of 3 wall chains, so a situation like this hyperbolic triangle. Then this curve in here is negative for canonical class, just because it's touching one point on a wall chain. So it's very easy to compute. This has to be negative. Yes?
Just to understand, you have a -7 because you are blowing up several times on the 3 points?
Yes, so here 3 times, here 2 times, and here once. So it's mine.
Why do you have a K² equal to 1?
It's because, so there is a formula so this is the minimal resolution of that. If K² is something here, then to compute the K² here, you add the length of all the wall chains. So here is -10, and I think that I added 11, because here you have 3, 3, 4, and 1, 11, okay? Yeah. So now, when you forget about this -4, you have a negative curve, like this. This is a gamma minus, like in here. And also, self-intersection is negative. How you know that? Because you are passing through this singularity, you contract, and then this is 2, phi 2. This is a cyclic quotient singularity. This is negative. That is telling you that this is negative. And it's actually a flip. So here you start the EMMP, this machine. That is how it starts. And now you run the machine, and you will see a picture like this. So this is the beginning. There you have the -4 and these 3 chains. And that minus means negative curve. Everything that is white without any number is a -1 curve. So you do the flip. The first one is a flip. Now you get this positive curve for canonical class. This is the usual flip that I explained, I think, yesterday. And now you can see that this -1 curve becomes a negative curve with respect to canonical class, so you flip. Now you see the positive, this negative appears, you flip again. How was this? Concentration. Okay? And now you flip, and then you flip again. So you have 1, 2, 3, 4 flips. And now in here, you can compute canonical class, and you realize that this is nef, finitely nef. And actually, this is telling you that the minimal resolution of that surface is so the smoothing of these two singularities, which is the minimal resolution of this surface, is a Dolgachev 2-3 simply connected surface. So you see that in the boundary, so when you have this point and you smooth, and you smooth 3 of the points and you stay with only this curve, then there is a new point that is a Dolgachev surface. So you go from this rational surface to a Dolgachev surface. But I just wanted to show you how the machine goes.
You mentioned that there is, in this Mori algorithm, there were like a variance that was dropping. This is why,
Yeah, you see that. So if you compute the indices for these singularities, you will see that the indices are dropping, and then you compute here that the canonical class is F, so you stop. Yeah. And there are no divisorial contractions in this situation. It turns out, I don't know, if maybe you can find sometimes some divisorial contraction, but in this case, you don't. So that is how this works. Now I think that I wanted to, so this is how this is run. I would like to go to these two situations very soon, but I want to do a summary of what I have said during this week. And also, I would like to add an extra application that has to do with these exceptional vector bundles, just to show you a little bit more. So this is the summary. So we have these W surfaces that are typically constructed in this way, so very abstract. You have a bunch of rational curves, you do blow-ups, you contract, and you try to compute obstruction. If obstruction is 0, then you have a situation like this. Typically, it's like that. But it's not necessary. Maybe the obstruction is not 0, but maybe you have a situation like that, but it's difficult to guarantee that you really have it. So typically, you have obstruction 0.
Jack, can I ask you something?
Yeah.
How do you know from the only curves that you ever have to worry about are the curves that you have from the beginning?
No, yeah, that is a very good question. So what I do is so you go step by step. It's like trying to guess the -1 curve on a non-singular surface. So it's not really clear. You might write the canonical class in an effective way, for example, then you know that in the support you have these curves. But in principle, it's not really clear. You're asking me why I have this.
Why is it left at the end of the process?
How do I prove that? Yeah. So the way you prove that it's Neff is that you have the canonical class here, you pull it back to that situation, and now you have the discrepancies and the canonical class of this thing, which is kind of negative because this is a rational surface. But then there are some tricks where this negativity is eaten by the positivity of the discrepancies that now are in the other side. And so you have an effective Q divisor. And now if something is negative, then you just try these curves and check that doesn't happen, so you have something Neff. And then for ampleness, well, here I'm not saying anything about ampleness, so. But we use the Nakai-Murchison if we want ampleness. Okay, so you have that these invariants are constant. If KW is Neff, then this is a minimal model. If Neff and big, then we have this canonical model with only T singularities, which is the replacement of this ADE. Even when you have obstructions, it is a challenge to construct these W's with KW big and Neff and K square large. So I don't care about obstructions there, just construct something, for example, a big problem is to try to construct something with something rational, a W rational with K that is big and Neff and canonical class as large as possible, 6, 7, 8, for example. And then you will be constructing exotic blow-ups of CP2 at few points. Exotic blow-ups means that you are constructing something that is homeomorphic to the blow-up of CP2 at a few points, but the diffuse structure is not, so they are not diffeomorphic. Something exotic is like exotic spheres, it's the same thing. So some Yeah, homeomorphic, but not diffeomorphic. That is exotic definition. Okay, I also told you that maybe you are motivated to describe what is going on in this moduli space. So say you fix invariants like PG0 and K squared between 1 and 4, which is the zone where you have the chance to prove that there are no obstructions in your example. Sometimes there are obstructions, but you have the chance to have no obstruction. And then a computer can search and find that horrible amount of possibilities for Wahl singularities in this zone. And by the way, something that I didn't say is that if you construct a W that has only one Wahl singularity and you have no obstructions, then this W is moving on a divisor in this compactification. So you have a divisor. So you have the maximal dimension for a degeneration here in the boundary. And so you can think about this number, for example, for 2,104 for K squared equals to 3 as 2,104 boundary divisors, at least. Maybe you have more. And what is the problem to analyze the situation is that typically all of these surfaces that appear here are rational. And I told you that rational is the hardest case. Well, what I was saying here, that when you have a W surface, then there is an explicit, this is very explicit way to do flips and divisorial contractions, and you really can find these canonical models and everything. And there is a new fractal picture over these minimal W surfaces that I will explain with these other endings of the MMP. Yes? These numbers is what we have found. No, we don't. So it's something that I mentioned here, that this problem. So even bounding singularities for a fixed K squared, like in that case, is kind of hard. Now, when it's not that rational, we have these bounds, so we can produce in principle a list of these. For these singularities, I was telling you that for Horikawa surfaces, we classify everything, for example. But it's not easy. There are new techniques that you need to classify that. But the really hard surfaces are the W's that are rational. When it's rational, I don't know any bound. So give me an exponential bound. I don't know. I would like to see something and then work out our techniques to see if we can improve that. So that is a big problem. Another connection, as I say here, is that you can construct, when you have a degeneration like this, you can construct exceptional collections of vector bundles from P1 chains on W. So let me explain that. And this is going to be at the end of the notes. I haven't worked them out yet. So this is the situation. So here we have the W surface. Here is my W inside of a threefold, and here is the WT. And now on the singular one, suppose that we have this chain of P1s, and we have these Wahl singularities on the nodes, and also say that this W has geometric genus 0, and the irregularity also is 0. And an extra assumption is that there exists this A, which is a Wahl divisor, which is a Cartier for all the rest of the singularities everywhere in the surface, except here, that is a complementary toric boundary to this gamma 1. And all the gamma i's are toric boundaries on the singularities. So you see the picture? So if you resolve minimally, then you see only one big chain. Okay? So to produce this A, there are techniques. For example, if you have that the fundamental group of the complement of the singularities is trivial, then one can prove that this A exists. Okay? So those are the hypotheses. And then for each singularity, we have a Hacking exceptional vector bundle. So Paul Hacking constructed them. And of rank Ni, which is the n of the Wahl singularity. And not only that, but there is an exception. So if you have this chain, there is an exceptional collection that goes from E0s to ER on the WT, an exceptional collection. And that means that when, so maybe we can put it here. That means, so these are exceptional vector bundles. So X, I, E, 0, well, I bigger equal than 1, EE, EC. And now in the collection is exceptional if you have that X, I, so for any I, E, J, E, K, E0 for every I, where the J is bigger than K. So when you move, so you have a E, J, you move it to the, oh yeah, sorry. J less than K. So you move an exceptional vector bundle from here to any other of these and compute X, any X, this is 0. Okay? So you have that. And now, so you see there is something extra over there. So you don't need the extra to say this. But now, if you have this extra part where this chain contracts to a cyclic quotient singularity, and so you have this deformation, which is coming from the contraction. And now you also have that this WT bar, which is the general fiber here, is the same as the WT you started with. So there are no any contractions at this level. Then you can say more. Then these gammas that you saw are part of an orbit of such geometric situation where flips and anti-flips on gamma I have the effect of mutate the exceptional collection among them. So you might think you have this chain. Now I will use these flips to produce other gammas, and then you have other collection. So what is the effect? There is a mutation. And with the mutation, you have exactly the same, the hacking exceptional vector bundle on the mutation. And then you keep going.
You don't need the curve A to do that.
Oh, that is a part of the hypothesis. So I need the existence of that curve A. And then, but on the collection, yeah, I don't do anything with A. A could have some maybe high genus. It's not rational. It's something that you prove that exists.
Then the A is needed for the existence.
Yeah, we need the A for the existence of this. Yeah. And so there is like a dynamics. Like you have these orbits. And now the group that is acting here is the break group. And since we have this hypothesis that this is isomorphic to that, so you might think about this as a, you run MMP and you need to reach a positive situation, which is the M resolution related to that. So here you have a deformation component of the cyclic quotient singularity, and this is happening over there. But for that deformation component, you have this P resolution. And actually, you can reach that by using MMP. So if it's negative, then you replace it with positive, and this has to reach eventually this positive M resolution. And so when that happens, you have that the corresponding exceptional collection has this property, that all X are 0 except for 1 in the positive side. But then there is a way to talk about this negative side, and where all the curves intersect negatively the canonical class or 0, and something else that I don't want to mention now, because you have infinitely many possibilities for this W minus if you just require that. So you need something else. And then for that collection, you have that the X for K that are not 0, everything is 0. And so this is a strong exceptional collection. And this is part of my a paper with Genia, 2022, that is called Categorical Aspects of the Kolar-Sheffer-Barron Correspondence, and will be part of my notes. And there are open problems too related to this. Okay. So this was the parenthesis on exceptional vector bundles and collections, in case you are interested in that. And now I want to go to the endings of MMP. So we have two situations. So at the beginning, I was telling you about the minimal models. So we have this, and we have the moduli space there. But now I would like to tell you about this situation and that situation. So assume that you don't have a curve like this. And so, but canonical class is still negative, so you need to have a curve like that. And then you can prove that this W is non-singular. So when you arrive to that particular ending, then the W is not singular and you have a smooth deformation. But this smooth deformation is not a smooth deformation of ruled surfaces, and doesn't need to be trivial. It's not like constant on fibers. For example, you might have that the general fiber is F1, which is something rigid, but can deform to F2n plus 1, to any odd number. F1 can go to this, and this could be an end of the MMP. So in that case, there are no Wahl singularities. You have a situation like this. So what happens to the other case? That is the one that I really like. So ending with so gamma minus square is positive. Then the WT has to be P2C. And then how about, so what are the possible W's? So maybe you can go further and have this question. What are the degenerations of the complex projective plane with only quotient singularities? And you don't impose anything, so just quotient singularities. And then, as far as I know, this is the short history of that. So this started with Badescu in 1986. He wrote a paper where he was studying what are degenerations of rational surfaces in general. In particular, he found some properties for degenerations of CP2. Fabrizio told me that he discussed this problem with Badescu, and then he came back. I think that he was in Italy, and he had this student, Marco Manetti, and he told him, well, he's doing this, and it is a bit of a mystery what happens with the projective plane. And then he studied that problem and wrote a paper in 1991, and he discovered many other properties. For example, if you put quotient singularities, then they must be Wahl singularities, and at most 3. But he couldn't classify them, really. And then finally, Hakin and Prokhorov in 2010 classify everything. And those are going to be the Markovian planes. And this is the picture, so this is the theorem. So any such degeneration of P2C is a partial Q-Gorenstein smoothing of this weighted projective plane, P A squared, B squared, C squared, where A squared plus B squared plus C squared is 3ABC. And that is the Markov equation. And so the picture for this moduli of CP2 is that you have CP2, P2C, and then you have this fractal situation. This is the Markov tree. And so think about a vertex or a Markov triple as a projective plane with these weights, and then you might degenerate to that vertex, or you might smooth everything except the singularity corresponding to A. So you are here, or you are here, or you're here, or maybe you want to have both singularities and then you are on these edges. Now, why this is the Markov tree? Because if you go from this point to that point, then you can prove you have a mutation, exactly. So this is a P1, there is a P1 that is connecting these 2 points. So, and what is happening with this P1? So you are smoothing the singularity with respect to C, and now you have only two singularities, and then at some point you obtain another singularity which corresponds to this C prime, and this C prime is exactly 3AB minus C, which is the mutation. So precisely the picture that you have for the Markov tree appears in this moduli space of CP2. So you replace P2 by these degenerations as an ending, okay? How this Markov shows up? Well, I told you that the K squared remains constant. So K squared for projective plane is 9, and you can do the computation for this other weighted projective plane, and you obtain this number, you simplify, and you see Markov equation. That is how it appears. And also, via the exceptional collections of Hacking bundles, you can obtain, using this, another picture of the well-known exceptional collections of length 3. So they generate the whole derived category, the bounded derived category of the projective plane, using these Hacking bundles. Okay, so this is another way to have the same picture. To finish, so now I will use the board again. I would like to tell you about the birational geometry of a Markov number. But this is kind of strange because this was the end of the MMP. So there is no birational geometry. We finish, right? So I would like to tell you what is going on. Let me see. Yeah. So now I will use the board. I have like half an hour, right? I will drink water too. I don't know, also questions? No?
So what are these ranks? What are the ranks?
The ranks are as always, are the indices of the singularities. Maybe I should remark that when you have a situation like this, where you satisfy this Markov equation, a very easy exercise tells you that the three singularities that you have are Wahl singularities, and the indices are A, B, and C. So the ranks are A, B, and C. How to build it? Oh, you have to go to the paper of, of Paul. Yeah, that is something, you know, there is a construction where he does a weighted blow up. There is an inductive construction, but this is kind of involved. It's not something I can do here. Okay, any other question before I go to the birational geometry of a Markov number? No, this is general. So the theorem can be used for any situation. For example, here you have a way maybe. Let me see. So you see this chain is connected with this P1 to this other chain, which is connected to this with this other chain. So now you need to produce this A, that I think that you can do it, or maybe you can start. You can end with this. Let me see. But you know there are ways to produce that. But in here you might have 3 bundles out of this deformation in a collection, in an exceptional collection. On Dolgachev surfaces, for example, we worked out that. You can see it at the end of the paper, and we can construct the longest possible exceptional collection for any Dolgachev surface, except for 2, 3. A Dolgachev surface is an elliptic fibration with 2 multiple fibers that have multiplicity that are coprime. So we call them DPQ. They have to be coprime. Then we produce for any Dolgachev surface with P and Q coprime. So any Dolgachev surface, exceptional collection of length 10. I think that this is the maximum possible. Except for 2, 3. We have length 10 for 2, 3, but we know that we can increase. That can be, so there are longer. So you can get 12.
That is not involved with the entire derived category, is it? This is not a full collection.
It's not a full collection, no. No, it shouldn't be a full collection. If you have a full collection, right, then it should be rational surface. a conjecture. There are always phantoms in these situations. Okay, any other question before I go for the birational geometry of a single Markov number? Okay, then I will do it. So let us consider the smallest Markov number to have something very simple at the beginning. And the smallest, so except 1 would be P2. So let us go for 2. That is the next. So say that the Markov number, we call it C, is 2. Then for that number, so you need to find the A and the B. You know, whenever you have a Markov number, there should be a triple where this Markov number is the biggest. And in this case, would be 1, 1, 2. Markov conjecture says that this triple should be unique. In this case, it's simple, in general. Now, then we have P2C degenerating to P 1, 1, because 1 squared is 1, and then 2 squared, 4. And so this is the contraction of the -4 curve on the Hirschenbruch surface F4. So you contract this -4, then you have this Wahl singularity. There is only one. So the picture would be like this, 4. Okay? And this is an end of the MMP. So what is the birational geometry here? So very simple. You will blow up a generic point on this deformation. And then I will have F1 degenerating to a blow up P of P1, 1, 4. So the picture is something like this, -4. And then this point is some point here. So then when I have the blow up, I have a -1 curve and -1 curve. So you see the picture, right? So now in this situation, you have, so of course, this is the minimal resolution. I'm here. This is my W. And now I have two extremal rays. So one is this one, and the other one is this other one. And if you consider this one, of course, you will blow that down, and then you will return to this. So we don't do that. We consider the other one. And the other one is always a flip. So there is gamma 1, gamma 2. This gamma 1 goes back to this picture, but gamma 2 is a flip. Flipping curve. So in here, you have a situation like this. Here is the 4. And now the images of these curves is something like this, and there is this -1 that is crossing this 4. This is my gamma 2. And this is flipping. So you can compute gamma 2 dot k is -1 plus 1/2, which is -1/2. And also it's negative. So gamma squared is negative. Okay, so we do the flip. This is the simplest flip. So what you do, remember you have a situation like this with a 4. This has to be over a cyclic quotient singularity. And the cyclic quotient singularity is very simple. You contract it, you have -3. So that is the one. So you go to 1, 3, 1, 1. Minimal resolution of this is a -3 curve. And now you need to think about what are the p resolutions of this. There is only one, minimal resolution, -3. So this is the gamma plus, and this is the gamma minus. And this is the flip. So you flip, and you get a deformation of F1 into F3. And this is it. And so this is the birational geometry. of this Markov number. Okay? Now we'll go to 29 to give you a better, bigger picture. So for 29, again, I need to find a triple where the 29 is the biggest. So C equals 29. Then the triple is 2, 5, 29. This is Markov triple. And now I have P to C degenerating to P, 2 square, 5 square, 29 square. And it turns out, and this is the key. Turns out that the minimal resolution has a particular geometry. And all the time is the same geometry. So what is the geometry here? I will show you in a picture. So this one has index 2. So this is the quarter 1-1 singularity. This is my -4. This is minimal resolution, by the way. Okay, minimal resolution of this weighted projective plane has this form. -4, -2, -2, -2. This is going to be the 29. This is the minimal resolution corresponding to 29. This is -10. And then you have 2, 2, 2, 2, 2, 5. And after that, you have 2, 2, 2. So the one corresponding to 5 is 2, 2, 2, 7. These are all wall chains. You can do the computation. You can check that we have these wall singularities. And now the connection here is a -1. And here the connection is a -1. So what you see here is a P1 fibration with 2 singular fibers that you can blow down. So now blowing down like classically, blow down. I mean, on the fibers, you blow down this -1, and so on until you get 0. You will get 0. And I will blow down the ending curve is going to be this, and here that one. So I will go to 0, 0, -10. And this is here simple. So vibration over P1. And that is the geometry. Very particular for these particular weighted projective planes. And so you do the same. So before, the trick was to blow up a point, a general point on the degeneration. Here is going to be the same. You have F1 going to the blow up the point of this. And what you see, so maybe let me use this same picture.
The 0, 1 is the -2 here, right?
Sorry?
The one that becomes the 0 is the first -1. The component is the one that meets the -10, right?
This, the last one, let me check. Because I choose, at the end, you will have a situation like this, and I will choose to blow down this one. So I don't, 5, and then I don't blow down that, I blow down the 7, I think. And then I have this blow up on a point. So let me use the same picture. I will do, this is minimal resolution. And now you have a situation like this. So gamma 1 and gamma 2. So it's exactly the same. These are going to be extremal rays. This gamma 1, if you choose that, then you come back. So you use the other one, which is flipping curve. This is flipping. Curve. And now you run MMP. So then run MMP. And now I will show you the picture, because now it's more complicated. It's not like you do one flip and you finish. Remember that we need to get into a picture where F1, well, it turns out there are no divisorial contractions. You will see only flips, and these flips are going to be unique. So you do a flip, you will have a positive curve, and there is a negative curve, unique one, and this is flipping, and you do it again, and again, and again, and again. This is unique. And this will go to F7. This is the end. But I didn't show you what happens in between, because I have a picture for that. Too complicated to do it here in the blackboard. So I was explaining this, and now you should have the picture. So you see, you have the minimal resolution, then you have the blow up. That is why you see 2 dots over 10. And I don't use the upper dot, but the lower that has a minus. This is flipping. You do the flip, and then this chain breaks into 2 chains, and you have the plus. And then the minus appears over there, and this is unique. The other one doesn't work. And you continue. Then you have a plus, a minus, you continue. You have a plus and minus. So there is 1, 2, 3, 4, 5, 6, 7, 8 flips. And you end with a 7, 0, 0. Okay? Okay, so the question is now, what is the MMP? So this is the MMP of a Markov number. So is it possible to describe what is going on for the whole Markov tree? Yes, we have always. Yeah. Exactly, yeah. So you have that triple, yes, exactly. And here you also have that. You can prove that you have it. Yes. Yeah. So in the degeneration, in here you have a situation to construct this exceptional collection of 3 vector bundles for P2. You can write it down. You see the Chern classes, and you compute. And, yeah. Okay, so now I want to make sense of the MMP. I want to explore what is this MMP for the whole Markov tree. So MMP for the whole Markov tree. Let me see what I have. So in general, you will see the same picture. So this picture is a general picture. And actually, we use here some theorems of Manetti that describes what are the minimal resolutions for this particular weighted projective planes. So it is always the case that you will have a situation like this. And you can prove that it's always the case that you have a minus 10 here. It's an easy exercise, by the way. And no other. So that is the general. Here you have the wall chain corresponding to A, the wall chain corresponding to C, which is the biggest Markov number, and is always crossing. So this this wall chain has always a 10, must have a 10, like that. And then you have the corresponding to B. Now you have the generic blow-up, so you have a situation of F1 going to this blow-up at one point of this weighted projective plane. There are 2 options, divisorial contraction, but if you do divisorial contraction, you come back to the degeneration of P2, or you have a flip, and then we go for the flip. So is it possible to make sense of the MMP on the whole Markov tree? That was the question. What are the connections between Markov triples? Is there a new way to think about this Markov conjecture using what you see from this MMP? Those are kind of questions, and this is what is happening. You start with a situation like this, that you have flip, flip, flip. Say that this W0 is the weighted projective plane. Okay, I'm not taking the other partial resolutions, always the weighted projective plane. If that happens, you can prove that you will go to F7, to a deformation to F7, like bounded, like always F7. One question, so you have the flips, so you have mu of them. Can you say something about mu? Does it go to infinity? I don't know. Is it bounded? Or can you describe a bit? So let me, maybe here I have the Markov tree so that you remember. You remember this Markov tree that was in my first talk. These are all the Markov triples, and I put colors for the Markov numbers that govern the triple. So blue is for 1, red is for 2, green is for 5. You have that. Okay. And then I will show you one theorem, which is next, I think. So this is a theorem, and by the way, this is in my paper with my student, Juan Pablo Zúñiga. So this is the birational geometry. Geometry of Markov numbers. And for example, and this is something that I like a lot. So you see, when you fix a Markov number like C, you need the A and B to have this Markov triple that I will use to run MMP. But when you have this ABC, then you have 2 branches. You know, like the color for green, you have these 2 branches for 5. Okay? And then, so pick any of these triples on this yellow part. So what does it mean? Branch means that you keep C, and then you mutate the others, like keeping C. And there are 2 ways to do it. That is why you have 2 branches. That explains why you have 2 ways. Then it happens that when you run MMP for all of these triples, this MMP stabilizes at the 3rd flip. So you do 3 flips, and then you go to the same surface. So you're going far away, you do 3 flips, and you go to the same surface. So moreover, when you go to that particular flip, particular flipping situation, when you go, when you go to this flip, you don't see exactly the same, You see a Mori train. So this branch of so you have this branch, like C, M0, M1, then C, M1 and 2, and so on. You do 3 flips, and you will see a Mori train. So you replace this Markov situation by a Mori train, and this Mori train is over that particular singularity. So this is over 1 over delta 1 omega. And delta is that particular number, C squared. C, remember, is the Markov number that you fixed. C squared, D, which is 9, C squared minus 4, and there is a C minus 1 squared. You can compute that. And then omega is this other number where everything depends on C except this number, which is the weight corresponding to the Wahl singularity of C. So the Wahl singularity corresponding to C is something like this. So that number is this C, so the A of the Wahl singularity. So imagine a situation where you compute that in the 3rd flip, you have a situation like this, and this doesn't depend on that number. Then you solve Markov conjecture immediately. But unfortunately, this number appears, and so we cannot say much about it. Well, we can say some things about it, and from this situation, after the 3rd flip that we see a Markov train, a Mori train, then we can explore these equivalences that I told you the first day, that there are 3. Everything is related to this cyclic quotient singularity, to what is happening here, or to what is happening in this surface. after you realize, after the birational geometry told you that this is happening, you can prove everything like with numbers, is combinatorics. And then you have the equivalences. Now, something to finish that is kind of beautiful is that, maybe I put it here, is that the delta of this Mori train, so there is a particular Mori train. So what I said is that you have this Markov tree, and now every color, you know there is a Mori train. There is a Mori train behind it. Also, if you want to run MMP and wondering, so how many steps I need to, how many flips I need to perform to arrive to F1 to F7, then if you want to go, so if you keep blue, then this number is constant. It's a particular number. You don't go to infinity. Although this goes to infinity, this number is a certain number. So to go to infinity, to have as many flips as you want, you need to change colors all the time. So you go from blue to green, green to, and so on, and then the number of flips goes to infinity. That is something that appears in the proof. So you go deep and deep when you change colors, when you change the Markov number. How many times you do that, that is something else. And now, then you have this Mori train for the branch, and the delta, you remember delta was the intersection with canonical class times the indices of the singularities. So that is delta. This is the delta of the Mori train, the little delta. And then this delta is exactly 3 times the Markov number, 3c. And so you have this infinite continuous fraction, which gives you that number. So there inside, you see this d that appeared in the previous, this d that appeared in here that computes the delta and the omega. And that d, as I say here, is exactly the discriminant of the Markov forms of the old Markov theorem. So I started this with a Markov theorem, like 130 years ago. And that Markov theorem is about quadratic forms. And then he has to define these particular forms that correspond to Markov numbers. So you have a particular form, and the discriminant is exactly this number. And there is much more. So conversations with with Cesar, for example, these Markov forms appear on this Hilbert space of endpoints in P2, which is also amazing. It's like you see it. Why the Markov form appears there, why the discriminant appears here. So you can find more, of course, in the paper with Juan Pablo. And then this is the last question of my mini course. So what is the Markov picture for other W surfaces? For example, what is the Markov picture for F1? So say that the general fiber is F1. What are the possibilities for W? What is the picture there? What is the fractal you want? And it's much more difficult. So Juan Pablo, for example, is studying that. Or what happens to any Hirschenbruch surface in these degenerations? Or to any surface. We would like to understand what is happening, how these singularities appear. Okay, so maybe that's it. So there are some dots here. Thank you very much.